This is Hugo de Garis, who's speaking at the Humanity Plus Hong Kong conference this December. So, Hugo, can you tell us briefly who you are and what you do?
Uh, my name is Professor Hugo de Garis. I have to explain a little bit. I'm an arcing mathematical physicist. And what I mean by arcing is ARC, that's after retirement careering. So I'm in my 60s. I expect to live another 30 odd years. That's a big block of time. So I've switched careers. So I talk about the wage-free third of life. So that's what I'm in now. And before I was director of the Artificial Brain Lab at Xiamen University in China, and I've been conventionally retired for about a year. I spend my time now studying intensively mathematical physics, pure math and math physics, looking into the possibility that there might be a femtotech. So that's a technology at the scale of the femtometer. That's 1,000,000 times smaller than a nanometer. A nanometer is 10 to minus 9 of a meter. That's about the scale of molecules. Whereas a femtometer, that's 10 to minus 15 of a meter. That's right down at, say, well, nucleus, nucleon, quark, that kind of scale. So I'm just basically sniffing around. I'm studying all these PhD level math physics books, pure math and mathematical physics books, trying to find phenomena that just might be applicable to creating a technology. So computing and engineering, that kind of thing, at these tiny scales. And the reason why femtotech would be so interesting would be if it can be done. Think about it. It's 1,000,000 times smaller, right, than nanotech. Therefore, its overall performance level, if it can be done, would be a trillion times greater than at the nano level. And the reason for that is, well, everything's 1,000,000 times denser, right, closer together. So the density would be 1,000,000 cubed times more than nano.
So, nano is 10 to the minus 12, and femto, skipping pico, is 10 to
Yeah,
the minus
okay.
15.
So why have I jumped from nano to femto? Well, the simple reason is that nature does not provide anything at the pico scale. Pico is 10 to minus 12. That's 1,000 times smaller than nano. There's just nothing there, because if you look at an atom, so an atom is what, roughly, say, 10 to minus 10 of a meter. And what's smaller than an atom? Well, then you have to go down to the nucleus, right? And how big's a nucleus? Well, it's roughly 10 to the minus 15. So it's 100,000 times smaller. There's just nothing in between. There is no picotech. I mean, I can imagine if you put enough components at femto scale, if you put enough of them together, you could probably, thousands and thousands of them, you'd probably get up to pico scale. But effectively, you're using femto scale components. So really, logically, you have to jump from nanoscale to femto scale.
Mm.
And then, of course, you can speculate, well, imagine, I don't know, a decade or so from now, we have the beginnings, at least in theory, of a femtotech. Well, then you can speculate that other people start thinking about, well, what's the next thing? Atto, ATTO, that's like 10 to the minus 18 of a meter. Could there be an attotech? And I think the next one's what? Exo? I'm not sure. I
Well,
haven't
what
learned a
sort of
lot.
applications do you think you'd find for femto technology first? I mean, what will be the first inroads to femto technology that we'll be able to engineer and use as a productive solution to some problem in society?
Well, that's one of the things I'm trying to look into. Uh, you know, there's nobody out there doing this kind of stuff. I mean, I'm pretty well on my own as far as I know. So if I had a really interesting answer to that question, I'd be off to Stockholm probably. So it's all very tentative at the moment. I can give you some possible answers. For example, when I talk about femtotech, uh, I'm seeing two major branches, two kinds, broad categories of tech. One is computing, computation, and the other one is engineering, putting bricks together, building stuff like that. Now, I'm an IT, information technology type guy. It's my background. I used to be a computer science professor. So I'm starting with computing. So one of the ideas I'm toying with right at the moment is, could I somehow make logic gates, as in computer science, and gates, or gates, not gates, that kind of stuff? Could I map that, translate that into phenomena in a branch of particle physics called QCD? That's quantum chromodynamics, and that's the theory of the strong force, the strong nuclear force. So I'm basically now fishing around, trying to find phenomena within QCD that somehow I might be able to translate into implementing these three basic gates, and or not. Because if you can do that, then you can compute. Because there's a famous theorem in computer science theory that you can perform any Boolean logic operation using those basic three logic gates. In fact, you can do it with just one, a so-called NAND, N-A-N-D, not and logic gate. So that's the sort of stuff that I'm trying to look at the moment. And if I can get it to work, then at least in theory, we've got the basis for a femtoscale computation,
Wow,
which is interesting.
sounds
Now,
very interesting.
I'm toying with the idea of writing a book about this. I'm hoping, sort of half expecting, that there'll be a whole bunch of possible ways to implement, femtoscale engineering and femtoscale computation. So I might write a chapter each on each topic, each way of doing things, and hopefully have that. The aim is, firstly, go sniffing around, find phenomena that might be useful, and then clarify it in my head, and then write about it, and then perhaps also within the book, set up a whole new alternative computer science course, teaching course, because one thing that's clear already is that if there is to be a femtotech of computation, then the whole curricula of computer science will need to be changed, radically changed. Future computer scientists will have to become mathematical physicists. I mean, that's clear already, because the scale dictates that you're talking about quarks and gluons and elementary particles and deep quantum mechanics, that kind of stuff. That's inevitable.
Cool. Well, we'll look forward to seeing you talk about all that at the conference this December. So I'll speak to you there, and after this we'll record a longer interview that other people might be interested in exploring later.